Okay, so we continue, and this morning, so we were the slide after this one. So I put again this one. So we discussed about phase matching. So delta K is equal to 0. And you remember we had in front of us this system of equations relative to the real amplitudes. And it's a case of phase matching. So delta K equals 0. And so that here you see that it depends only on sin delta phi. So no change in the sign of these quantities. And we also say that, we see here that we have a maximal energy exchange for delta phi equal plus or minus pi over 2. And, yes, okay. And so we saw the case corresponding to delta phi equal plus pi over 2. And we saw that it corresponds to the case of photon fusion here. Okay, so now let's move on the photon splitting. So in that case, so if, imagine that we don't know that it's photon splitting, we say, okay, what does correspond to delta phi equal minus pi over 2? And so in that case, so you replace delta phi by minus pi over 2. And so you see that dA1, dAz, dA2 over dZ is positive, and dA3 over dZ is negative. So it's exactly the case of photon splitting. And so, when again, we have the photonic picture here. And so the incident beam at omega 3 with the initial phase phi 3. So you a priori don't master this phase. It is phi 3. In practice, you don't know exactly what is this phase. But what we know, according to the previous equations, is that the phi at omega 1 at omega 2, so phi 1 and phi 2, has to verify, to fulfill this equation, phi 1 plus phi 2 equal phi 3 plus pi over 2. Same thing for the stimulated splitting. So here, phi 3 and phi 1 for the beam at omega 3 and omega 1. And so you will have, for the photons at omega 1, phi 1, and for the photon at omega 2, the phase will be given here by this, phi 2 equal to phi 3 minus phi 1 plus pi over 2. And now we can imagine an experiment. So we have chi2 here, h bar omega 3, and yes, h bar omega 1. Imagine this experiment. So we have 3 incident beams in that case. So with here phi 1, phi 3, and phi 2. Now, if we are able, and in practice it is possible, not so easy but possible, to master the phases. You see here that according to delta phi, here you can have, so if you have delta phi equal minus, so imagine you can play with the faces and you set the faces at delta phi equal minus pi over 2. In that case, you are going to perform a splitting process. Now, if you modify the faces in order to fulfill delta phi equal plus pi over 2, you are going to perform a fusion. So by adjusting the faces, you can have some frequency generation or difference frequency generation. But in that case, compared to this, in these cases, nature does the work. But here, you will be the nature, so you have to master carefully the phases. But it could be an interesting experiment to study these phase problematics. Okay, and so now if we consider, so we come back to the generated intensity at omega 3 as a function of z, and so in the case of phase matching, according to the previous equations, so we know that we are going to have a quadratic evolution of the intensity. So obviously much more efficient than the out-of-phase matching case. And so you remember the coherence length LC is equal to pi over delta k. So it means that in the case of phase matching, we have an infinite coherence length. Okay, so now we are going deeper in this phase matching case. So you have here the expression of delta k. It's easy to replace the k vectors by as a function of the refractive indices. So you get this equation. You see that if there is no dispersion, so n3 equal n1 equal n2, so we write n this refractive index. So in that case, obviously, we obtain delta k equal n multiplied by the conservation of energy multiplied by 0. And so we see here that for a non-dispersive medium, phase matching is always fulfilled. But the problem is such a medium does not exist, or we have to work and to use metamaterials or other kind of more exotic things. But for classical medium, it's not possible. Even if you have a very small dispersion, I don't know, 10 to the minus 6, for example, you cannot fulfill this. So now I am going to show you why birefringence is necessary for achieving phase matching in a dispersive medium. We'll see that, as Professor Boyd said this morning, that we have also quasi-phase matching. But at first, let's begin with birefringence phase matching. And we are going to take the simple case of second harmonic generation. So omega 1 equal omega 2. You have here also the delta k equal 0, written as a function of the refractive index. And in the case of SAG, and in the case where the two waves at omega are in the same mode, so we have these simple equations. N at 2 omega has to be equal to n at omega. Okay, so let's consider an isotropic crystal, so a crystal that has a non-zero chi2, so you can be isotropic from the refractive index point of view, and you can have a non-zero chi2. I will come back to that point tomorrow evening. And so imagine that you want to make second harmonic generation in a cubic crystal exhibiting a chi2 tensor. So you consider the Selmayr equation, n as a function of lambda. And what do you see here? That for you have no couple lambda omega, lambda 2 omega, for which you can have lambda n at omega equal to n at 2 omega. It's impossible because you have these dispersions. So impossible to get phase matching in that case. Now, if you consider an anisotropic medium, if you consider a uniaxial or biaxial crystal, so now we know that in a given direction we have two possible values for the refractive index, n minus and n plus. And so in that case, you see here that, so imagine, so these two curves were measured or calculated in a given direction of the crystal. And you see here that for this particular couple of wavelength, lambda omega and lambda 2 omega, you see that we have n plus lambda omega equal n minus lambda 2 omega. It's marvelous because here we see that it's possible to fulfill the phase matching condition. So we say that phase matching is possible when the birefringency can compensate the dispersion in wavelength. Okay, so now we come back to equations. Here you have the phase matching relation. Here, so momentum conservation, energy conservation. If you combine these two equations, you get this. It's possible to calculate then the ratio between omega 1 and omega 2. This ratio is expressed like this as a function of the refractive indices. And then this ratio being necessarily positive, you can have two relations of order compatible with this. So n1 less than n3 less than n2, or n2 less than n3 less than n1, knowing that if we are in the case of normal dispersion, that is to say that n1 smaller than n2 smaller than n3 for mode plus and for mode minus, if we have omega 1 less than omega 2 less than omega 3. And so in that case, we know that we can fulfill phase matching for three configurations of polarization. So denoted here by E minus and in terms of E minus and E plus. And so you have three possible. So among the 10 to the 3, that is to say 8 possible combination of polarization, plus, 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 minus, 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 and so on, only 3 are possible. And type 1, so it's a problem of terminology, type 1 corresponds to the case where the two incident waves have the same polarization. And you see also here, you can understand that the mode relative to the higher circular frequency is a minus mode. That is to say, it corresponds to the smaller refractive index. Okay, and so you have type 1s, for example, for the SFG. So type 1 SFG, so the two waves at omega 1 at omega 2, we have omega 3 equal omega 1 plus omega 2, are in the same state. You see here that's the DFG at omega 1, that is to say omega 1 equal omega 3 minus omega 2, and you see here that omega 3 and omega 2 are in the same polarization state. So it's just a problem of terminology. Okay, same consideration can be applied for 4-wave interactions. So we consider, yes, the momentum conservation and the energy conservation, and only 7, we demonstrated that only 7 configuration of polarizations are compatible with phase matching among these two, the 16 possible combination of refractive indices. And so we have also give a number for each type, with the same idea to keep type 1 when the 3 waves that are summed or for which we have sum or difference frequency are in the same polarization state. So you can find the demonstration of this in this paper. Okay, so what about phase matching loci? So now we know exactly which configuration of polarizations are compatible with phase matching, but now what is the angular distribution of the phase matching directions? And so in the writing now I introduce theta pm and phi pm, the angle or spherical coordinates of the phase matching directions. And so the goal now is to calculate the phase matching angle. So it's what you have to do in your lab when you want to perform a parametric process. And here I take the example of type 1, second harmonic generation, in a negative uniaxial crystal. So in that case, so for example, if we consider the section of the index surface in the xz plane, so you have here the ordinary, so I just put here the two layers relative to the phase matching. So the phase matching condition says that we must have NO at 2 omega equal NE at omega. So I just draw here the two corresponding layers. So the it's a circle at 2 omega, because it is the ordinary index at 2 omega, and an ellipse and omega. And we see here, in this case, that you have intersection between the layer at omega and the layer at 2 omega. So here, this direction corresponds to a phase matching direction. And you have here the analytical expression of the angle, the phase matching angle as a function of the principal refractive indices. So it's exactly the way to calculate the phase matching angles. So sometimes there are analytical solutions and sometimes not. Okay, we also shown that, so by considering, in fact, relation of orders between the refractive indices, we have shown that the phase matching angle of type 1 is smaller than that of type 2, smaller than that of type 3. So here, yes, one point, and I will come back to that maybe a little bit tomorrow. So in uniaxial crystals, so the phase matching directions describe a cone around the optical axis OZ. It means that you have an infinity of directions fulfilling the phase matching relation. And so it's a cone, so you have something like this. So you have an infinity of direction here for which you have phase matching. And so you have, when it exists, because sometimes you have no phase matching conditions, but when it exists, so it is described by a cone. And so you see that the cone of type 1 is at a smaller angle than for type 2, than for type 3. So it's very important, because imagine you have observed a type 1 SAG in a crystal. If it's the case, maybe you can have type 2 and type 3, but not necessary, because in fact, the birth of the phase matching cones is in the XY plane. All the cones start, in fact, so if you vary the wavelength, it starts in the equatorial plane. And so, for example, if you imagine, you say, okay, I measured a phase matching angle of type 2 SHG. Obviously, you will have type 1. And if you observe type 3, obviously, you will have type 2 and type 1. So sometimes it can be interesting to know this little thing. Okay, in biaxial crystals, it's a little bit more complicated. And we have established that there are 5 geometries of cones. So here it is represented in a Wulff diagram. So it's very convenient, in fact. So you have X at this point, Y here, Z here. The theta angle is like this, and the phi angle like this. And so you see here, so I put here these 3 lines correspond to the 3 optical axes at the 3 wavelengths, lambda 1, lambda 2, lambda 3. And we can show that you have that kind of phase matching cone, this, so from xz to xy, from xz to yz, from yz to xy. So 5 possibility of junctions between principal planes. So it's a little bit more complicated. Okay, so we have finished with phase matching loci, and during my talk I only spoke on collinear phase matching, but obviously you can also decide or have non-collinear phase matching. So it's not so the concept and the philosophy is exactly the same. The only difference is that you have to take into account the angles between K2, for example, if we take Chi3 as a reference, so we take these 2 angles, and so you have this new relation. So nothing new. Okay. And yes, one point, important point, non-collinear phase matching exists only if phase matching is allowed. And so you can also demonstrate this. Okay, so quasi-phase matching. So just 2 slides on that. Marty Feyer will detail the things tomorrow. So in that case, the light propagates in a direction which is not a phase matching direction. And so there is a small mismatch. And if this mismatch is equal to the coherence length of, so it is realized so in artificial structure, so in a structure in which here we see that so we have a grating with a periodicity big lambda. And so if this mismatch k lambda is equal to 2 pi over big lambda, so in that case we have this relation here. You see that we can have this equal to 0, which is called phase matching, quasi-phase matching. So delta k is different, is not equal to 0, but so if in this structure, and Marty will explain that tomorrow, and I will come back to that also tomorrow from the symmetrical symmetry point of view. But you see that if you can make a reset of phase of plus or minus pi at each coherence length, you will be able to build, to have constructive interference at each coherence length. So we'll discuss this point. Marty will discuss this point tomorrow. Okay, so here, from a general point of view, you have no restriction. You saw that for birefringence phase matching, that only 3 configurations of polarization are allowed. So in some way, it's a restriction. But here, in the case of quasi-phase matching, you can access to all the configuration of polarizations. If you want one particular one, I don't know, E+++, okay, you have to choose the good grating to do that. But maybe it's not interesting to do that. Maybe it can be interesting. Okay, and just the last slide. So and there was a question this morning on that. So the 3 ways to tune quasi-phase matching. So the multi-grating, so you translate the grating, the fan shape, or the cylinder that we proposed several years ago. So you turn the crystal, or you translate the crystal, and you can vary, by this way, you vary the grating periodicity, and so you can vary the wavelength. Okay, so now let's move on angular, spectral, and thermal acceptances. And so for that, so we have to come back. We are going to see that these acceptances are relative to the parameters of dispersion of the refractive index. Let's come back to this sinquare function. So I3, so imagine that it's a sum frequency generation, and you plot the generated intensity at omega 3 as a function of delta k z over 2, and we know that we have a maximal value for I3 at delta k equal 0. And this can be, it is relevant for phase matching, birefringence phase matching, as well as for quasi-phase matching. And so this delta k equals 0 can be achieved at a given angle for a given triplet of wavelength and at a given temperature. So now imagine that we want to vary one parameter. We want to vary the angle. So it is exactly this curve. So it is the same curve, but now plotted as a function of xi. Xi here can be theta, phi, lambda, or the temperature. So you have also a sinquare function. This curve is not necessarily symmetrical because obviously in the argument of the sinquare here, the function of dependence of delta k is not a linear function. So you obviously it's not in the general case it's not symmetrical. So what is the acceptance with respect to the angle, the wavelength of the temperature? So these parameters is defined by this quantity L, the crystal length, multiplied by delta xi. And what is delta xi? Delta xi is here this length, that is to say the length between the xi pm and the first 0 of the function. So it is this distance here, and this distance, if you want to put it somewhere here on this axis, it corresponds to 0.405 of this maximum value. And so when you have this, so you can measure this curve, and so you measure the full length at 0.405, you multiply by the crystal length, and you have the acceptance. Okay. Acceptances versus dispersions. So we can define angular acceptances, L delta theta L delta phi. And so these angular acceptances obviously depend on the dispersion of the refractive index according with the angles theta and phi. So it's directly linked to the topology of the index surface, n as a function of theta and phi. The spectral acceptance, L delta lambda, is governed by the derivative of n with lambda, and the thermal acceptance linked with dn over dt. And obviously, if we have a small derivative, a small variation of the refractive index as a function of the parameter psi, we will have a broad acceptance relative to this parameter. So you understand now that the acceptances are k parameters because it's a key. These considerations are very important when you want to maximize the conversion efficiency. And so according to the divergence of the beam, so we will be in an optimized situation when the divergence of the beam is smaller than the acceptance L delta theta, L delta phi. The spectral line width of the beam smaller than the spectral acceptance. For example, if you want to perform a parametric process using femtosecond beams, so you know that you will have a broad spectral line width of the pump beam. And so in that case, it's absolutely necessary, if you want to involve all the Fourier components of the pump beam, you will have to have a huge spectral acceptance. And a way to have a huge spectral acceptance, or a huge angular or thermal acceptance, it is to consider a small crystal length. But if you have a small crystal length, you remember that the efficiency depends on the square of the crystal length. So it means that you have a compromise to find between the crystal length and the acceptance consideration. And so by the same way, when you have heating of the crystal due to absorption, typically you can have 2, 3, 4, 5, 6, 10 degrees at the center of the beam. And so you increase the temperature, so you have an increasing of temperature. And so obviously, if you want to have not too much losses, it's absolutely necessary that this increase of temperature be smaller than the thermal acceptance. And you know, this last point is very important. There were several crystals in the history of nonlinear optics who were marvelous from the Chi2 point of view. From the phase-matching point of view, so there were phase-matching directions, strong nonlinearity, but the thermal acceptance was of about few tenths of degree. It cannot work. It cannot work. Even so, okay, you can say, okay, I thermostate the crystal and so on. But in fact, from a real practical point of view, it doesn't work very well. So you have, it's a difficult sport because you have to fulfill a lot of parameters, and these acceptance considerations are very important. So it's, these are the key parameters for the choice of the good crystal and of the good direction of propagation. Okay, So we can make some calculations to quantify these things. And I am going to explain to you the notion of critical and non-critical phase matching or quasi-phase matching. And so for that, we expand delta k in a Taylor series of the dispersive parameters. So we know that because we want to define the acceptance, that it corresponds to delta k equal 2 pi over L. And so we write this Taylor series. And the case when the first order is equal to 0, it's what we call non-critical phase matching. And when it is different to 0, it is critical. It is called the critical phase matching. So you have here a calculation corresponding to critical to non-critical phase matching. And so we can calculate here the expression of the acceptance, the non-critical phase matching acceptance, and you see that it depends on the second derivative of delta k as a function of the dispersive parameter xi. Okay, now same calculation in the critical phase matching case, and you have here the expression of the corresponding analytical expression. And what we see here, and what you can see if you put some numerical values, that the critical acceptance is smaller than the non-critical acceptance. So it is clear that for any kind of applications, we are going to try to find non-critical phase matching situations. Okay, so I give you here an example. So it was done in my group in 2011. It's a case of, it was a new crystal at that time, CDSI-P2. And so this crystal is interesting because it is transparent up to, yes, in the real life, it is up to 6 or 7 microns. At the beginning, we thought that it was broader in the infrared. Okay, so here, and Patricia Segon will explain to you how we can measure all these phase matching directions. So you see here, so it's a case of second harmonic generation, type 1, type 2, and we have plotted here the fundamental wavelength, lambda omega, as a function of the phase matching angle theta. And you see that we have measured all these wavelengths for type 1 and type 2. And so I show you that because without any calculations, just by considering the phase matching curves, you can find the non-critical situations. Let's take this point here. So we have at theta equal 90 degrees. So it means that the phase matching direction is contained in the xy plane. So what do you see here? You see here that the derivative of lambda omega, so you have an horizontal here tangent. You see that the derivative of lambda pm as a function of the angle theta is equal to 0. And so it means that the corresponding angular acceptance is infinite. Okay, you see that even if you turn the crystal, you see here, you change a little bit the angle, not 90, but I don't know, 88, 87. You see that you keep here the phase matching. So you have to consider, yes, I cannot go on the screen because I will have some problem. But in fact, this curve has a thickness. And so you see that the thickness corresponds exactly to the acceptance. And so you see that even at 2 or 3 degrees, I don't know, far from this angle, you stay in the thickness of the phase matching curve. So you see immediately that here you will have an angular, non-critical phase matching direction. Now, if you consider a possible fluctuation, variation of the fundamental wavelength, you see here that you are going to lose immediately the phase matching curve. So here, at this point, it is very critical from the spectral acceptance point of view. And here, so you see that this phase matching curve is like this, and you see that at this point you have a vertical tangent here. So at this point, the derivative of the phase matching angle as a function of the fundamental wavelength is equal to 0, and so infinite spectral acceptance in that case, but very critical for the angular acceptance. So you see it's very, very simple to identify the interesting situations. And it's exactly the same for quasi-phase matching. So we made this experiment in MgO-doped pipeline crystal, and we measured all the direction in the crystal, in the pipeline structure, all the quasi-phase matching directions for second harmonic generation. So one more time, we have plotted here the fundamental wavelength as a function of the theater angle. And we have measured, for example, here you see at this angle, you have the corresponding curve given the second harmonic intensity as a function of the fundamental wavelength. And by measuring here this, the full width here, we can determine by the measurement the spectral acceptances. So it is this point, and you can do that for all these points, and we obtained this curve, and we show that, but it's not surprising, that the maximal spectral acceptance is obtained here at this point. Okay, and so some words about the anisotropy of the angular acceptance. Here, for example, so it's CSTIOAS04, so it's a crystal of the KTP family. And so you see, for example, here at this direction, so you have measurement and calculations here. So let's take this direction. So in that case, you have d phi over d theta, which is big, but d theta over d phi equal to 0. So it means that here you will have the angular acceptance relative to phi is bigger than that relative to theta. And it means that if you look at the beam, you have the second harmonic beam, you will have a strong astigmatism. You will have an astigmatism due to the anisotropy of this. So nonlinear optics is nice, but you can have some problems sometimes. Okay, and so let's finish this part with spatial and temporal Walkoff effects. Let's begin with spatial Walkoff. So you remember it is the angle between the electric field and the electric displacement, or it is the angle between the wave vector and the pointing vector. So this spatial Walkoff exists in uniaxial and biaxial crystals when the two polarization modes are excited. So mode plus and mode minus. So let's say that in all the cases, of birefringence phase matching, you will have Walkoff. Using quasi-phase-matching, not. You can have, but you can also choose to have no Walkoff. But if you have birefringent quasi-phase-matching, in the general case, not in other cases, we'll see that there are cases without spatial Walkoff, but usually you have spatial Walkoff. So in the general case, the pointing vectors of mode plus and minus are not collinear, and so we have a misoverlap between the interacting beams, and so some decreasing of the efficiency. Okay, so let's begin with type 1. So in type 1, so you have the incident beam, for example, here. I took the example where, so I consider a phase matching direction where the fundamental beam has an ordinary polarization. So it means that you have no deviation of this beam in the medium. And now if you look at the second harmonic beam, so you can keep the picture I gave you this morning, and so to consider section by section of the nonlinear medium along the direction of propagation. So here, typically, section 1, so the thickness is of about a few microns. And so you have all these, the dipoles that are created emits in this direction. It is the direction of the pointing vector. And if you consider another section, for example, this one, so the dipoles are here, and you will have emission here, so in this direction. So you keep the same directions for the pointing vectors, so at each place in at the different z position in the crystal. And at the exit, what do you have? So you have the fundamental beam here, and you see here the transverse evolution of the intensity. You have something very large. You see, in fact, that so it's not a Gaussian beam. You start with a Gaussian beam, but here it's not a Gaussian beam because it is completely, so you have a broadening of the transverse section of the beam. So it's typically the signature of type 1. So you know you can have astigmatism. You can have also that this broadening of the transverse section. So you have a spreading of the second harmonic intensity, and it takes place in the plane of the Walkoff. We can make some. You have also here the name of Dr. Boyd. The other one, in 1965. And so they made nice calculations. And we have these, typically this evolution. So I'm not going to go to give too much detail. So the important parameter is rho L over W0. Rho is the Walkoff angle, L the crystal length, and W0 is the radius. So it is it is calculated here under the plane wave approximation. So W0 is a radius of the beam. So you have this function, and you see here that if you plot the second harmonic intensity as a function of z, you see that you start with a quadratic evolution, and after that it is proportional to z. So it works very well. We had verified many times that kind of calculation. The case of type 2 is a little bit different than type 1. So I took here the case so it's a type 2, and so the one polarization is the ordinary one, and the other one is the extraordinary one. So you have here the two pointing vectors. Keep in mind that the wave vectors, the ordinary wave vector and the extraordinary wave vector, are collinear, because here we are in normal incidence, and the Snell-Descartes laws correspond to the wave vector, not to the pointing vectors. So we have, if you consider here, you are somewhere in the crystal, so the wave vector here so it's only the fundamental beam. I am somewhere, I can be here. So here I have EO, EE. If I look at the wave vector KO, KE, and you have also the pointing vector, yes, maybe you can, SO, and you have SE like this. So the two wave vectors are collinear, not the pointing vectors. And so imagine that we are in a case where the second harmonic wave is also an extraordinary wave, so that it is close to this direction here. So it's not exactly in the same direction, but very close. So what do we have in that case? So if you look at the exit of the crystal, you have something very close to this profile here. So a nice confined profile. But here we have a problem. We still have a problem. The problem you see here that over this distance, Zmax, you see that the two beams don't overlap. So it means that you have ordinary photons here, extraordinary photons here, but if we want to make nonlinear optics, the photons have to be present at the same time and at the same place. So if you are somewhere here, the photons cannot speak, so the medium cannot take one ordinary photon here, one extraordinary photon here, to give rise to an extraordinary photons at 2 omega. So it means that the process stops from Zmax. So you have a saturation of the process. So it can also, it was well modelized by Mehendal and Gupta. And so here, so they defined some relevant geometrical parameters. And obviously, we have something like this. So you have a quadratic evolution, then something which is close to a linear evolution, and then a saturation. So from Zmax, the conversion efficiency saturates. Okay. And so, yes, one important thing is that you have a saturation of all the acceptances. And so we studied this effect carefully in this paper. So it is clear that when you have Walkoff, usually you find acceptances that are broader because the effective length is smaller than in the case of a zero Walkoff. Okay, the previous calculations are in fact relatively simple. It's really more complicated in the case of focused beams, And Jean-Jacques Zondy made all this work a long time ago, and so he defined the relevant parameters here for that. And so in my chapter here, I took the modeling of Jean-Jacques, and I made a lot of calculations using this. And so here, F opt is the optimal position when usually in nonlinear optics, because we need intensity, and Bob explained that this morning. Usually we focused the beam, and there is an optimal position of the waist in the crystal. So F opt equal 0.5 means that you focused exactly in the middle of the crystal. And you see that for type 1, for example, the optimal is always reached when you focus the beam in the center of the crystal for each value of the Walkoff angle. But for type 2, it depends, and you see that you have here to focus the beam more closer to the entrance, so you can calculate very precisely these things, and it works. So if you really want to optimize the conversion efficiency, you have, so you can calculate, but you can also make the experiment and find empirically the optimal. But it's not in the middle of the crystal for type 2. Okay, and we made also very systematic calculations. So in these four graphs, we have the second harmonic generation efficiency as a function of the crystal length, of the beam waist radius, of the crystal length. So it is type 1, type 2, yes. So type 1, type 2, as a function of the crystal length, as a function of the beam waist radius for various values of the Walkoff angle. And you see that, for example, I don't know, we are not going to detail all these things, but you see here that when the Walkoff is equal to 0, you get much more efficiency, so 10 to the minus 5, compared, for example, to 10 to the minus 5. So you have a factor of about 8 between a situation, so here it's type 1, a waist radius of 30 microns, and so you have almost one order of magnitude of difference due to a difference of Walkoff angle of 2 degrees, and so on. So it's so you can check this in order to have the details of that kind of things. Okay, and we also proposed the Walkoff compensation by sticking 2 crystals. So you take, instead of taking a crystal of 1 centimeter long, you cut the crystal in 2 parts. You tilt the 2 crystals. You stick the crystals. So we can make that not using a bond, but by molecular adherence. And so here you see that maybe if we use the thickness of the beam, we see that, so there is an attenuation, but you see that in the second part of the crystal, it is very simple in fact, you increase the overlap of the 2 beams. And so, but you have to choose a good orientation and to have this pi shift of orientation. It works very well. Okay. Some words on temporal Walkoff. So for that we have to consider the group velocity, Vg, which is given by the derivative of k with omega, and so it depends obviously on the dispersion of the refractive indices. So if you know the Selmayr equation, you can calculate the group velocity at the different wavelength. You will hear about that in the talk of Majid tomorrow. You will see a lot of group velocity calculations and measurements. And in the case of normal dispersion, that is to say, when the refractive index increases as a function of the circular frequencies, then we have a negative here group velocity. And so what we have during the propagation, we will have continuous splitting between the two pulses. And so if you take, for example, Gaussian pulses, but you can also consider Lorentzian pulses, so you can calculate or measure so the temporal separation between the two pulses. And so typically, the delta t over z range between 10 femtosecond per millimeter and 100 femtosecond per millimeter. So it means, for example, yes, after 1 millimeter, if you are in this case, according to the group velocity mismatch, after 1 millimeter, the two pulses are completely separated. So you stop the nonlinear process. So I give here an example. So now in the space representation, we can calculate the distance where we have separation of the partial separation of the two pulses. And for example, here, if you have the green, so you have it's a case of second harmonic generation in KDP. So green gives UV, and with a picosecond pulse, a pulse duration of 1 picosecond. So after 7 millimeters, the two pulses are separated. Okay, and Marty Feyer will explain you this tomorrow, the way by using aperiodically poled crystals to reduce this temporal walk-off. So it's named the adiabatic frequency conversion. Okay, so now last part of this foundation of parametric nonlinear optics, I'm going to give you an overview of the main interactions. So I have to control the time. Patricia, so I end at 6:30 or 1 hour? Marvelous. Thank you very much. Okay. So let's begin with second harmonic generation. We start from, in the case of perfect phase matching and pump depletion. So it means that the conversion efficiency can be very strong. So we start with the three coupled equations. And using Manley-Rowe relations, so Manley-Rowe relations are very nice, and we saw that it allows to have a deep understanding of a nonlinear process, but it can also be very useful in calculations. And so using these Manley-Rowe relations, so here you see that we work with the square of the modulus of the electric field. So it's an energy relation, so it corresponds, in fact, to what we saw this morning, to the conservation of the total intensity at any position in the crystal. And so here we can analytically integrate the system, and we have these tangent tan hyperbolic square and sec square function as a function of z. So you will find details in this article of paper of Milton. And so here I have plotted so the fundamental, the total intensity at omega. Obviously, you have a decreasing here of this, and correlatively an increasing of the second harmonic intensity. So the question is to know if we are going to be able to reach 100% of efficiency. Theoretically, it's possible. And some guys made very nice work in very difficult situations. So here you have the conversion efficiency as a function of the input fundamental energy. So this work was performed in Bordeaux, in France, at the laser megajoule, you know, the laser for the inertial fusion. And so you see here very high energy, 300 joule per pulse. And so the fundamental wavelength is 1053. So the pulse duration is 12 nanoseconds. It's a top hat, because I didn't discuss about that, but the fact that you have a Gaussian or variation of the transverse profile will affect, in fact, the conversion efficiency. And so if you want to reach 100% of efficiency, you have absolutely to have a top hat beam, the most stable as possible. And so you see here that they used LBO and a very large crystal. And the diameter is 6.5 centimeters. At room temperature, so the crystal is given in the right phase matching directions. The thickness is 12 millimeters. And you see here that they were very close, so they reach 96, 97% of efficiency. And imagine, in that case, you have also thermal effects and so on. So a lot of things has to be fulfilled in order to get such a very high efficiency. Okay, so yes. Now, so we were in the case of perfect phase matching, delta k equals 0. Now, if you have a small delta k, I don't know, delta k equal 10 to the minus 4, 10 to the minus 5. So in that case, if you integrate this, also using Manley-Rowe relations, you get that these solutions, and one more time, we are speaking of the famous paper of ABDP of 62. So they made, in fact, this calculation, this general calculation. And so in that case, you express the second harmonic and also fundamental wave as a function of Jacobi, using Jacobi elliptic function. And so you have something, you have something periodical, so the periodicity is much longer than in the case of out-of-phase matching, but so it's so you build and then you have destruction of what you built. Okay, so now let's move on third harmonic generation. So in the case of the undepleted pump approximation, and so it's obviously generally the case because the chi3 is very small, so it's very difficult to have more than few percent of efficiency. So in that case, so the derivatives of the fundamental beam is equal to 0. so we keep here the derivative of the generated wave at 3 omega. And so it's very easy. So it's exactly the same calculations than in the case of second harmonic generation. And so you see here that you have a quadratic evolution of the efficiency as a function of z, and the efficiency depends on the square of the intensity. We made, and we got the highest value of efficiency in a crystal, and it's also higher than in an optical fiber. So you have here the energy conversion efficiency plotted as a function of the fundamental intensity. So you see here 40 megawatt per square centimeter in two crystals, KTP and TiO2 rutile, and you see that we can access to, in fact, so it's not easy to calculate the efficiency because you have energy here and intensity here, but it was typically 2 or 3, between 2 and 3% of efficiency, which was not bad for that. Okay, so now let's move on second order parametric fluorescence. So you cannot make any calculation if you don't make quantum mechanics in that case. You cannot use the system of equations I showed you because you need to know, if you want to use the system of coupled equations, obviously you need to know the amplitude of the field, the electric field, at omega 1 and omega 2 at z equals 0. You have to know the value at z equals 0. So in the case of parametric fluorescence, at z equals 0, you have 0 photons at omega 1 and at omega 2. But in fact, no. You have the quantum fluctuation of vacuum, and so you have some photons. And you can calculate this, so there are several ways to calculate the intensity of parametric fluorescence. The simpler one is this one, considering here, so the gold rule. And so I am not going to give you too much detail. In fact, this calculation was done with an efficient quantum model only in 2007 by Diane. And the results are a little bit different than using the gold rule. So what we show here is that, so it's a case of parametric fluorescence. So you have here the energy level diagram. Yes, so this morning I didn't comment about that. You see here that these energy levels are in dashed line, is to explain that, to symbolize that these energy level are virtual energy level. We could have here, for example, a real level, but in that case, we will have storage of energy. So usually when you are in a transparent range of the medium, so maybe the conduction band is somewhere, the level is somewhere here, but you see that we work here in the gap, no absorption, but the quantum description use these virtual levels of energy. So 10 to the minus watt, so it's not, and we can have also more, and so it's not so difficult nowadays to generate pairs of photons. It works very well using pipeline, for example, or other materials. And one more time, you will have the lectures of Robert Boyd, Gert Leusch, Claude Fabre on fundamental quantum optics. And so you will have more details on these calculations. So now on parametric amplification. One more time, we have the equations here. So the perfect phase matching, in the case of perfect phase matching and undepleted pump approximation. So the pump beam is at omega 3, and we have also the evolution of the two beams at omega 1 and omega 2, the signal and idler. And so we have two cases when we are here, two cases to consider. E1 equals 0, E2 different from 0. So it's a case where you want to amplify the beam at omega 2, and E2 equals 0, not E1, so you want to amplify the beam at omega 1. And in that case, so it's not difficult to show that the intensity at, so it's easy to integrate this, and it is described by sin hyperbolic square and cos hyperbolic square, and the argument is proportional to z. So you have this, that kind of evolutions. And in the argument here in beta, so you have the kappa 1, kappa 2. In fact, the nonlinearity is here. And you see here that you have also the pump electric field. And it's exactly the same, the symmetrical equations in the other case where E2 is equal to 0 and when you have amplification at omega 1. So you see here that you amplify, so here you have I2 at the entrance of the crystal, non-zero, and you have amplification. And here you see that for the population at omega 1, 0 photons at the entrance of the crystal, and you have generation. All these things work very well. And we did 2 years ago this experiment, so it was done also in the laser megajoule in Bordeaux. So we made here an experiment of parametric amplification using 5 pump beams. So, you know, when you want to work with very high energy, you can say, okay, I built a very big laser, very big beam with a lot of energy, and usually it's very difficult. You can also say, okay, I can buy some smaller laser with smaller beams, and if I combine all these beams is a given nonlinear crystal, can I reach the same efficiency than these with a very big beam? So we made these heavy experiments. And so here the crystal is put in a oven here. So we have to keep the temperature fixed. And so so the incident beams, so the 1, 2, 3, 4, 5 beams here are green beams. And we wanted to amplify this red beam at 725 nanometers emitted by an OPO. And what we got, we succeeded. You have here the parametric gain defined like this. So it's a ratio between the energy of the amplified signal divided by the energy of the input. And so you see here that we reach a gain of about 60 using here 0.62 millijoule, and you have here the efficiency. And so it's the best efficiency ever reached in such configuration. So you saw also that we were in a non-collinear configuration. It means, and we spend a lot of time to do that, that we had to optimize the non-collinear phase matching configuration. So one more time, a lot of calculations and experiments to validate the model, and the final experiments where we succeeded. So 27% of efficiency, and so the pump energy, the five beam, each having 33 millijoule, so it's a total energy of 165 millijoule. The input signal energy, the red beam, was 2.2 millijoule, and so the output was 50 millijoule. So we were happy of this result. Okay, the third order parametric amplification. So it's a little bit more difficult. So I'm going to consider the case of perfect phase matching and the general case of depleted pump approximation. So one more time, you recognize here the system of the four coupled equations, and so also there are different possible configuration if you want to stimulate using one mode, and if you want to double stimulate. So we made this study, and so as for three-wave couplings, it can be described, well described, using Jacobi elliptic functions. So it's a little bit heavy, but it works, and you open the good book of mathematics and you will find the nice Jacobi elliptic function. So you have a huge family, but very, very useful. And so we made the classical, it was not done previously, the classical theory of the third order parametric amplification, and we made also the experiment. And you have here, for example, the generated energy at omega 1. So the triplet, so here it's a stimulated splitting, stimulated over on two modes. And so it's a stimulated third order parametric fluorescence. And so here we have measured and calculated. You have the calculation here, and it works very well. So we had to work hard to obtain such a good agreement between calculation and experiment. So the generated energy at omega 1 as a function of the pump energy for this energy for the stimulation beam. It was done in a KTP crystal. The crystal length is not so big, 1.3 centimeter. And you see here that the pump beam was a green beam at 532, the stimulation beam in the infrared at 1.6, and the beam not initially present at the entrance of the crystal was a beam at 1.47 microns. So it's a stimulation of a triple photon generation, the two triplets, wavelength being these wavelength. So you will have some details here, and I'm not going to speak about all the quantum work we did on that during this school, but maybe I will put, when we will send you the slide, I will put the reference of our quantum papers on that. Okay, optical parametric generation and oscillation. And so, yes, let's begin. So, about terminology, the way that omega 3 is written omega p, p for pump, omega 2 for the signal, and omega 1 is the idler. So you can choose. Omega 1 can be the signal and omega 2 the idler. You remember this morning I gave you this picture of cascading of parametric fluorescence and optical parametric amplifications. And so here you have the general expression given the signal and idler intensity, so as a function of z, and you recognize here the sec and ch and sh square functions corresponding to the amplification of the signal and idler. And so you can calculate these things, but one more time, if you want to calculate this, IS fluo, II fluo, it's necessary to perform the quantum calculations. From this step, we can estimate the intensity you can generate through this process of parametric generation. Usually the efficiency is very weak, and so it's why it's interesting to work in the picosecond and femtosecond regime if you want to make such parametric generation experiments. But we will speak about that tomorrow with the talk of Majid Ebrahimzadeh. Okay, and so it's an experiment here of optical parametric generation in the BBO crystal. So it was done by Petrov, and Valentin will also give you a lecture next week, and it's an example of a nice experiment of optical parametric generation. So Valentin will give you some more details on that. And also, now let's move on optical parametric oscillation. So here, probably Majid is going to recognize one of his nice drawings. And so if you want to increase, because we saw that the efficiency of parametric generation, so you have in the progressive, you have only one trip in the crystal. But, and so usually the nonlinear crystals have a length not exceeding 1, 2, or 3 centimeters. So if you want to increase the crystal length, artificially increase the crystal length, it's exactly as for a laser. You put the crystal inside a cavity, and by this way, you can achieve round trips of the light in the cavity. So it's what it's drawn here. And so you have the pump here, and you make round trip, several round trips of the light in the cavity, and then you can increase the interacting length. And you have two, but Majid will explain to you in details tomorrow, two configurations. In the CW and nanosecond regime, you can use a simple cavity like this, but in the pico and femtosecond regime, it will be necessary to use synchronously pumping scheme, and you will have all the details tomorrow. Okay, so the interest of OPOs, at first the generation, you can generate obviously beam at fixed wavelength, but you can also generate tunable beams. It is obvious that it is a strength of parametric fluorescence. You have here so the incident photons, and you see here that you can generate this. I write H A omega 1 H, not H, H omega 1 A H omega 2 A. You can generate this, and so on. So you can see that you can generate a continuum of pairs. And for all these pairs, you have energy conservation. So by tuning, in fact, by modifying the refractive indices, you can modify the phase matching conditions, and then you can generate efficiently a continuum of pairs of photons. And so I will tell you again that you have the lecture of Majid Ebrahimzadeh tomorrow, and Majid also wrote books on that topic, so I recommend you to read these books. Okay, and one of our last results, so it's tunable OPOs using pipeline crystal. So it's in the nanosecond regime. The frequency, the repetition rate is at 10 Hertz. We pump at 106. And here the idea, so I show you the picture in a previous slide. If we want to have an infinite angular tunability, we can cut the crystal as a cylinder. And so it's what we did here in a very thick pipeline crystal fabricated in Japan in the group of Takunori Taira. And so here this big pipeline crystal, so it's you have the pipeline structure, the grating structure. We cut a partial cylinder. So the aperture angle is typically of about 30 degrees, corresponding to the full angular range for achieving phase matching in pipeline. And so because we are in the nanosecond regime, so it's not so difficult to make an OPO, we put the cylindrical crystal inside two mirrors, and so we got here, you have here the generated wavelength, so the signal here in the lower part, and the idler on the upper part, so you have the generated wavelength as a function of the phi angle. It means, for example, if you turn the crystal at phi equal 20 degrees, you are going to generate the signal at 1.5 and to generate the idler at 3.5 microns. So it works very well. And you have here really the strong interest of optical parametric oscillators. Okay, so I have finished my talk, probably because I am hungry, not hungry. And so it's good news because you can ask questions. And so here, so tomorrow I will give you a lecture, a small lecture on symmetry aspects, tensorial calculations aspects. Some parts are classical and other parts are originals. And so it will be tomorrow evening, so it will be difficult. And so here you have a picture of Grenoble, so it's not so far from here. So you have here Beldon. So Institut Néel is here. So this place is called the Presqu'île Scientifique. So here 6,000 people are working. So you have the Atomic Agency Center here, The CNRS is here. You have here the ILL for the neutron facility. So it's a European facility, and also the European synchrotron is also here. And so Néel Institute is somewhere here. Okay, thank you very much.